Have you ever pondered the staggering power of the bombs that have shaped our world's history? Welcome to a journey into the intriguing world of explosive power. Today, we delve into a topic that has not only altered the course of our history, but also continues to shape our present and future: the difference between atomic, nuclear, and hydrogen bombs. Each of these bombs represents a significant leap in our understanding of physics and holds a unique place in the annals of human ingenuity and ambition. They are an embodiment of our ceaseless quest for knowledge, albeit a chilling one considering their destructive capabilities. First, let's consider the atomic bomb, the pioneer in this explosive trilogy. Born out of the turmoil of the Second World War, the atomic bomb was a result of the groundbreaking Manhattan Project. It harnessed the power of nuclear fission, where a heavy nucleus like uranium or plutonium is split into two, releasing a massive amount of energy. Next came the nuclear bomb, a term often used interchangeably with the atomic bomb. However, there is a crucial difference between the two. While atomic bombs rely solely on fission, nuclear bombs utilize both fission and fusion. Fusion involves the combining of light atomic nuclei, such as hydrogen, to form a heavier nucleus, and this process releases energy far greater than that of fission alone. Finally, we have the hydrogen bomb, the most potent of the trio. Also known as a thermonuclear bomb, it operates on the principle of nuclear fusion. It's essentially an atomic bomb wrapped inside a hydrogen bomb, creating an explosive force thousands of times more potent than the bomb dropped on Hiroshima. The development of these bombs over time has been a testament to our scientific prowess. Yet it also serves as a stark reminder of the immense responsibility that comes with such power. Dive with us into the fascinating and somewhat terrifying world of these powerful explosives. As we peel back the layers of science, history, and politics intertwined with these bombs, we hope to shed light on their distinct characteristics, their evolution, and their impact on our world. Our journey begins with the birth of the atomic age. It was a time during the throes of World War II when humanity, in its desperate pursuit of survival and dominance, unlocked the destructive power hidden within the heart of matter itself. This was the dawn of a new era, a period defined by an extraordinary leap in our understanding of the universe and our ability to harness its forces. In the mid-20th century, in secret laboratories scattered across the United States, an ambitious project was underway. The Manhattan Project, as it was known, brought together some of the finest minds of the time. Their mission? To develop a weapon of unprecedented power, the atomic bomb. And the key to this power was a process called nuclear fission. Now, nuclear fission might sound like a complex term, but the idea is deceptively simple. It's all about breaking things apart. Imagine a heavy atomic nucleus like that of uranium or plutonium. Apply just the right amount of energy and you can split that nucleus into two smaller ones. This splitting releases a tremendous amount of energy, millions of times more powerful than conventional explosives. But it doesn't stop there. Each fission event also releases additional neutrons, particles that can trigger more fission events. This creates a chain reaction, a rapidly escalating cycle of destruction that culminates in a blinding flash and a devastating shockwave. This is the fundamental mechanism that powers an atomic bomb. Yet, the story of the atomic bomb is not just about science. It's about the choices we make as a species, the paths we choose to tread. It's a stark reminder of our capacity for destruction, but also our ability to seek knowledge, to explore, to understand. The atomic bomb, a monumental leap in destructive power, was just the beginning. It marked the dawn of the atomic age, a chapter in our history that would forever change the face of warfare and the course of nations. But as we'll see, it was only the first step on a journey that would lead us to even more powerful forces waiting to be unlocked. As science pressed forward, so did the evolution of destructive power. The atomic age was just the beginning. As our understanding of the atom grew, so too did the scale and scope of our weaponry. We moved from atomic to nuclear bombs, a shift that represents a leap in both power and complexity. Let's take a moment to clarify something. The term nuclear is more encompassing than atomic. You see, all atomic bombs are nuclear, but not all nuclear bombs are atomic. Sounds confusing? Let me break it down. Atomic bombs, like those dropped on Hiroshima and Nagasaki during World War II, rely on nuclear fission. This is a process where the nucleus of an atom is split into two smaller nuclei, releasing a huge amount of energy. But nuclear bombs can also use nuclear fusion, where two light atomic nuclei combine to form a heavier nucleus, releasing even more energy. nuclear bombs are generally more powerful than their atomic counterparts. They have a two-stage design, the first being a fission bomb and the second, a fusion device. The fission bomb, or primary, is used to create the extreme conditions necessary for the fusion, or secondary, to occur. This is why nuclear bombs can be hundreds, even thousands of times more potent than atomic bombs. The largest nuclear bomb ever detonated, the Tsar Bomba by the Soviet Union, had an estimated yield of 50 million tons of TNT. That's over 2,000 times more powerful than the atomic bombs used in World War II. But it's important to remember that this immense power doesn't just have destructive potential. It's the same energy that powers our sun and other stars, and could be harnessed for power generation if we can learn to control it. With the advent of nuclear bombs, mankind had harnessed a power that could both destroy and create. The evolution from atomic to nuclear weaponry is a stark reminder of the dual nature of scientific advancement. As we push the boundaries of our knowledge, we must also grapple with the ethical implications of our discoveries. From the nucleus of an atom, we leap to the power of the sun. As we delve into the world of hydrogen bombs or thermonuclear bombs, we find ourselves in awe of their tremendous power, which significantly surpasses that of their atomic and nuclear predecessors. The hydrogen bomb's development can be traced back to the late 1940s and early 50s, a time when the world was in the grip of a Cold War. The quest for a more potent weapon led scientists to explore nuclear fusion, the process that powers our sun and stars, as a source of destructive energy. In essence, a hydrogen bomb works by using an atomic bomb as a trigger. The immense heat and pressure generated by the atomic explosion kickstarts the fusion of hydrogen isotopes, resulting in an explosion of an unfathomable scale. The energy released is several magnitudes greater than that of a nuclear fission bomb. What's fascinating about this is that the process mirrors the natural phenomena occurring in the heart of our sun. The sun, a gigantic ball of gas, primarily made up of hydrogen, continuously undergoes nuclear fusion. The intense gravitational pressure at its core forces hydrogen atoms to come together, creating helium and releasing an enormous amount of energy in the form of light and heat. This is the same process harnessed in a hydrogen bomb, albeit in a much more destructive manner. The first successful test of a hydrogen bomb, codenamed Ivy Mike, was conducted by the United States in 1952. The detonation obliterated the Pacific island of Alujilab and left a crater more than a mile wide. The shockwave was felt over 700 miles away, and the mushroom cloud reached an altitude of 20 miles. The explosion was 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The hydrogen bomb, the pinnacle of destructive power, is a testament to the terrifying and awe-inspiring power of scientific advancement. When harnessed responsibly, this power holds the potential to illuminate the universe. But in the wrong hands, it can also cast the longest and darkest of shadows. Now, let's unravel the differences that set these bombs apart. Atomic, nuclear, and hydrogen bombs, all formidable in their own right, each operate on unique principles and have had varying impacts on our world. Starting with the atomic bomb, the first of its kind, it relies on a process called nuclear fission. This is where the nucleus of an atom is split into two smaller fragments, releasing a considerable amount of energy in the process. The atomic bombs dropped on Hiroshima and Nagasaki during World War II demonstrated the devastating power of this technology, forever changing the course of history. On the other hand, a nuclear bomb, while also employing fission, incorporates an additional step. In this two-stage process, the initial fission reaction triggers a secondary, much more powerful fusion reaction. The fusion process involves combining lighter elements to form heavier ones, releasing an enormous amount of energy. This extra step greatly enhances the destructive power of the bomb, making it many times more potent than an atomic bomb. Now let's turn to the hydrogen bomb, the most powerful of the three. This weapon also operates on the principle of nuclear fusion, but with a twist. It uses isotopes of hydrogen, deuterium, and tritium to produce a fusion reaction. The energy released is so immense that it dwarfs the atomic and nuclear bombs. The first successful test of a hydrogen bomb, codenamed Ivy Mike, was carried out in the early 1950s and marked a significant escalation in the arms race. The development and usage of these bombs have left indelible marks on our history and society, leading to political tensions, arms races, and a more acute awareness of the destructive potential of scientific and technological advancement. Yet, they also serve as stark reminders of the power of human ingenuity and the dual-edged sword that is scientific progress. Understanding these differences not only enlightens us about our past, but also casts a light on the potential future of scientific and technological advancement.